So guys, we shall use Feynman technique to solve this integral. So let us first introduce a and let I a equals integral 0 to infinity e to the power minus x square sine ax square upon x square dx. So we have introduced a here in this sine term. When we put a equals 1, this integral is transformed into the original integral. So first we evaluate IA and then we put a equals 1 in this integral to get the original value. Now differentiate both sides with respect to a. So we have d I a dA equals d dA integral 0 to infinity e to the power minus x square sine ax square upon x square dx. So we have this I dash a equals, now by the Leibniz integral rule of differentiation under the sign of integration, this becomes 0 to infinity and this differentiation becomes partial differentiation. This is converted to partial differential e to the power minus x square sine ax square upon x square dx. So we have this I dash a. Now we differentiate this term and we get e to the power minus x square upon x square, and here we have x square cos ax square dx. So the differential of sine term is this cos term. So when we differentiate sine with respect to a, we get this term. So this is equal to 0 to infinity e to the power minus x square cos a x square dx. So we have the value of I dash a equals integral 0 to infinity e to the power minus x square cos ax square dx. Now we know that cos is the real part of exponential term, and this exponential term for which the real part is cos x is e to the power iota ax square dx. So the real part of this exponential term is this cos x. So this is equal to real part of 0 to infinity e to the power minus x square bracket में 1 minus iota a dx. So this is the value of I dash a. Now we have to evaluate this integral. Now we know that if s is any complex number such that the real value of s is non-negative, then the value of the integral 0 to infinity e to the power minus sx square dx is 1 by 2 square root of pi over s. So here we see that if s is a complex number satisfying this condition, then we have this integral. Now here our integral is very much similar to this. Here we have s equals 1 minus iota a. So e to the power minus 1 minus iota a x square dx, and the value of this integral is 1 by 2. We put the value of s as 1 minus iota a and we get this value. So now we have this integral. Now if we put this value here, then we get the value of I dash a as real part of this 1 by 2 and square root of pi upon 1 minus iota a, and this is square root of pi by 2 real part of 1 minus iota a whole power minus 1 by 2. So we have this value of I dash a. Now if I integrate both sides with respect to a, integrating with respect to a, we have integral of this, and we have integral I dash a dA equals square root of pi upon 2 real part of integral and 1 minus iota a whole power minus 1 by 2 dA plus some constant of integration. Now the value of this integral can be calculated easily. So we have square root of pi by 2 real part of, and the value of this integral would be 1 minus iota a whole power 1 by 2 upon 1 by 2 minus iota plus c, and 1 upon minus iota we know, and we know that this integral becomes ia, and this is equal to square root of pi by 2. 2 get cancelled by this 2, so we have real part of 1 upon minus iota, that would be iota square root of 1 minus iota a plus c. So ia equals this. So in order to calculate the value of c, I put a equals 0 on both sides, here and here. So in order to calculate the value of c, I put a equals 0. So I0 equals square root of pi real part of iota and under root 1 plus c. Now the real part of this imaginary number is 0. Therefore I0 equals c. But the original integral gives I0 equals 0 to infinity e to the power minus x square sine 0 x square upon x square dx. Here I substitute the value of a 0 and this is equal to 0. So I0 is 0. Therefore I0 equals C and it is equal to 0. So I0 equals C equals 0, but I want the value of C, so the value of C is 0 here. So we have this value. Now if I substitute this value of C here, I get IA equals, substitute this value here, this value is 0, the value of C is 0, so square root of pi real part of iota under root 1 minus iota A. So we have evaluated the value of IA. So I have to calculate the value of the real part of this number. So first I put A equals 1 on both sides because the original integral is equal to I1. So if I substitute 1 for A, I get I1 equals square root of pi real part of iota and 1 minus iota here. Now I have to evaluate the real part of this complex number. So I use polar coordinates, the polar transformation. So I suppose 1 minus iota equals r cos theta plus iota r sin theta. This gives r cos theta equals 1 and r sin theta equals minus 1 on comparing both sides. Now this gives r equals square root of 2 and theta equals tan inverse minus 1, that is minus pi by 4. So 1 minus iota equals r and the value of r cos theta plus ir sin theta would be r e to the power I theta by Euler's theorem. So we have r e to the power I theta, that means square root of 2 e to the power minus iota pi by 4. So this is the value of 1 minus iota. Okay, now if I put this value here, I get I1 equals square root of pi real part of iota square root of 2 e to the power minus iota pi by 4 whole power 1 by 2. This is the value of this complex number here. So this is equal to square root of pi real part of iota square root whole power 1 by 2 e to the power minus iota pi by 8. And this is equal to square root of pi and the value of square root of 2 whole power 1 by 2 is 2 raised to the power 1 by 4 real part of iota cos pi by 8 minus I sin pi by 8. Here I again used the value, the Euler's formula. So this is the value of I1. Now if I calculate the real part here. First I multiply iota inside the bracket and I get this value as sine pi by 8. So this is the value of I1, but I1 is the original integral, that is the integral 0 to infinity e to the power minus x square sine x square upon x square dx, and it is equal to square root of pi 2 raised to the power 1 by 4 sine pi by 8. So we have this value of the integral. Thank you.